Lunar mining sounds simple until reality hits. $200 million launches, tiny payloads, no profit. Elon Musk just revealed how Starship solves this. Mass driver railguns launching moon-made satellites electromagnetically. Build there, manufacture there, launch there. No rockets. So what makes Starship the key to unlocking this revolutionary method? Before we talk about solutions, let's establish what we're actually working with. China's Chang'e 6 mission brought back samples from the moon's far side last year, and scientists found something unexpected: fragments of Ci chondrite meteorites containing water. This was the first time this material had ever been confirmed on the lunar surface. What makes this significant is that Ci chondrites are incredibly fragile. Less than 1% of meteorites found on Earth are this type because they rarely survive impacts. Yet the moon preserved them for billions of years. Then researchers discovered something else. Lunar soil contains far more nitrogen and volatiles than solar wind alone could explain. The answer turned out to be fascinating. Earth's atmosphere has been leaking into space for eons, and the moon's been catching it. Our magnetic field funnels atmospheric particles outward, and with no weather or erosion, the moon just accumulates this material. What looked like a dead rock is actually a 4.5 billion year storage vault, so the resources exist. Water, ice, helium-3, rare Earth elements, all confirmed by multiple missions. The question isn't whether the moon has valuable materials. The question is, why hasn't anyone built a mine yet? This is where engineering reality gets brutal. Launch costs destroy the economics before you even start. Traditional rockets charge $2,000 to $10,000 per kilogram to low Earth orbit. Getting to the moon costs more. Even if you successfully mine helium-3 worth billions, you'd spend hundreds of millions just transporting it back. The math collapses immediately. Then there's the scale problem. Current lunar landers carry maybe 100 to 300 kilograms to the surface. Industrial mining needs excavators, processing equipment, power systems, habitats, tens of tons minimum. With traditional rockets, you'd need dozens of missions costing $100 million each. The timeline stretches to decades, budgets balloon to tens of billions, and the whole plan falls apart. But the real killer is return economics. Mine valuable materials, spend a fortune launching them back, then compete with Earth sources that have zero transport costs. You can't win that equation. Seattle-based Interloon is developing an excavator that processes 100 metric tons of lunar soil per hour to extract helium-3. Impressive engineering, and they're targeting a 2027 mission. But they face the same transport barrier everyone does. This problem has killed every serious lunar mining proposal for decades. Then there's Starship, and this is where everything shifts. SpaceX's fully reusable vehicle can carry over 100 metric tons to the lunar surface in a single mission. That's more payload than all Apollo missions combined, delivered across the entire program. One Starship flight equals years of traditional missions. The reusable design could drop costs from $200 million per launch down to $2 to $10 million once the system matures. That's not incremental improvement. It's a complete economic reset. What does that actually enable? You can deliver an entire mining complex in 1 or 2 flights. NASA already proved the concept this year with their Prime 1 experiment. Honeybee Robotics' Trident drills successfully extracted lunar soil samples, demonstrating the technology works. Now scale that up. With Starship's capacity, you could deliver multiple drilling systems, Interloon's excavator, power generation, and robotic processing equipment in a handful of missions instead of decades. The timeline compresses from impossible to realistic. But here's where Musk's thinking gets genuinely revolutionary, because Starship doesn't just solve transport. It enables a completely different approach to the entire question. Traditional thinking says mine resources and bring them back to Earth. That model keeps hitting the same wall. What if you flip it? What if you mine materials to use them on the lunar surface? This is where the mass driver comes in. It's essentially an electromagnetic railgun that uses magnetic fields to accelerate objects to extremely high velocities. On Earth, atmospheric drag and strong gravity make this impractical. But the Moon has 1/6 Earth's gravity and virtually no atmosphere. You could accelerate payloads to lunar escape velocity, 2.38 kilometers per second, using electromagnetic force alone. No rockets required. Here's the complete vision. Use Starship to deliver factory equipment and robotic systems to the lunar surface. Those systems mine regolith and process it into raw materials. Then manufacture products directly on the Moon, specifically AI-powered satellites. Use lunar metals for structure, lunar silicon for solar panels, even lunar oxygen for propellant if needed. Build complete satellites using almost entirely local resources, then load them into a mass driver and launch them electromagnetically into orbit. Look at what that does to economics. You're not paying Earth launch costs anymore. You've bypassed the return trip problem because nothing comes back. The products stay in space where they're needed. Once this system runs, the marginal cost of each satellite drops to basically the energy for manufacturing and launch. With solar power readily available in space, that's nearly free after initial infrastructure investment. The system becomes self-sustaining. Mine materials, build products, launch them, generate revenue, reinvest in expanding capacity. Growth compounds exponentially. The physics are solid. Mass drivers have been studied since the 1970s, when physicist Gerard O'Neill proposed them for space colonization. The technology works. We've just never had infrastructure capable of building one. Starship provides that infrastructure. It can deliver the superconducting magnets, power systems, launch rails, and control electronics needed. Manufacturing with lunar resources is harder but not impossible. We've demonstrated small-scale in-situ resource utilization already. Scaling up is an engineering challenge, not a physics barrier. Now, for the honest assessment. This isn't happening next year. Starship is still in test flight phase, improving with each iteration, but not yet at the operational reliability needed for repeated lunar cargo missions. SpaceX is working through heat shield performance, orbital refueling, and landing precision. These are solvable problems, but they take time. Meanwhile, China is moving systematically forward. They've completed Chang'e 1 through Chang'e 6, including the first-ever sample return from the far side. Their crewed lunar program is officially underway, and the 2030 timeline for landing astronauts remains on track. At October's Shenzhou 19 press conference, officials confirmed that preliminary design work is complete for the Long March 10 rocket, Mengzhou spacecraft, Lanyu lander, and lunar spacesuits. Launch facilities and tracking networks are under accelerated development. The U.S. Artemis program, originally targeting late 2024 for returning astronauts, has faced repeated delays due to technical and budget challenges. At December's Senate hearing, Jared Isaac Mann warned bluntly, "If we fall behind, we may never catch up." When House Science Committee experts were asked if NASA could return before China, responses were stark. "No, I am very pessimistic, and no possible way with the present plan. So China will likely land astronauts first. That's the realistic assessment. But does that determine who wins long term? Landing first demonstrates technical capability and carries symbolic weight. But the real competition is who establishes sustainable, economically viable operations. Who builds infrastructure enabling permanent presence and resource utilization. That's where Starship's capability becomes decisive. China's Long March 10 can deliver roughly 27 tons to trans-lunar injection, respectable for crewed missions, but a quarter of Starship's capacity and not reusable. Every Long March 10 is built from scratch at full cost. SpaceX's reusability changes sustained operations fundamentally. More payload per mission, higher flight frequency, dramatically lower cost once mature. China recognizes this gap. Their space program has acknowledged that limited launch capacity remains a key bottleneck, and they're working on reusability but years behind SpaceX's development. This gap directly impacts who can industrialize the moon faster. And that's the engineering breakthrough making Musk's mass driver vision viable, not just the mass driver itself, but the transport system capable of actually building it. Without Starship's payload and cost reduction, lunar mass drivers remain theoretical. With Starship, they become buildable infrastructure. Once that exists, space economics shifts from Earth-dependent to truly independent. 3 problems killed lunar mining: launch costs, scale, return economics. Starship solves all 3. Reusability cuts costs, massive payload delivers infrastructure, mass drivers eliminate returns. Build there, launch there. That's the breakthrough. Thanks for watching New Space Review. If this analysis helped, hit like and subscribe for space engineering coverage you can trust. What's your view on electromagnetic launchers? Share below.